Yeah, we're not at inverse yet. That's a couple pages away, or maybe a page away. So here's my matrix A. I get my matrix B. Locked on me. 4, 2, 3, and then matrix C. Again, 2 by 2. 1, negative 2, negative 1, positive 2. So matrix A times matrix C. That gives me that. Then matrix B times matrix C. And they give you the same result. And there's another place to put it. It's a strange relationship, because you think, you have equality here. AC equals BC. C is common to both sides, so you would think that A and B would be the same as one another. But it's pretty clear here that A and B are not the same matrices. Right? So it's a relationship that works. It is what it is, but it's not something you would necessarily expect. All right, but again, easily verifiable. The obvious case here in 3, AB, product of A and B is equal to 0. If that's the case, it's not guaranteed that A equals 0 or B equals 0. All right. But I think they're both a 0 matrix. Because I don't want to. I'm getting carpal tunnel here. I don't want to type anymore. Yep. 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 Going the other way. Yep. 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 All right. So, in typical algebra, old school algebra, you would think, or you would know anyway, that in order to get a zero product, that's why we have the zero product property, the foundation of all quadratics, that in order to get a product of 0, one of the two factors has to be equal to 0. And maybe both of them, maybe just one of them. In this case here, you could get a product equal to 0, the zero vector, zero matrix, without either of the two matrices that make up the product, the two factors, without either of them being equal to 0. Okay, so that's somewhat surprising. Number 4, the power of a matrix. You're not going to apply the power of 3. What do you do? Just cube each part? It's the same as matrix multiplication, just over and over again, right? So, but, there's all sorts of little caveats here. But it's basically telling us if I have a to the p power, so a to the third power, find a times a times a again. Right? So, but the good news is you can do that, just working off of the one matrix in your calculator. So, do it that way. Oh, wrong. Calculator understands order of operations better than we do, so it knows to actually carry out the 2 by 2 matrix multiplication first, then multiply by the matrix again. It also understands the power property. All right, so let me just vary something very slightly here. Let me make this a say -3. Yeah, different question, yeah. But. All right, so basically what this is telling us is where, in multiplication, when you multiply matrices, you can't just multiply corresponding parts. If there's a particular order to things, there's an algorithm. But when you're actually raising it to a power, it works the way you would think. So what I was saying before about it, can we just, raise each part to the 3rd power? I don't know. Let's see. So it looked like, after testing it with a couple of values, it looked like we could test it by changing my my first entry to a -3. That is definitely -3 cubed. So what we're looking at, and if you're still unconvinced, because maybe it's like along the main diagonal it works, but not along the, or not at the other locations. So I put like a -4 there. You could, if I just ask you to do an operation, you could do it on the calculator. So, yeah, so we run into a little bit of an issue here because we have along the main diagonal, the relationship holds. Right, but you see when I put in a -4 here, and then cube it, -28 is not -4 cubed. Right, so we're looking at something that works only along the main diagonal, right? And we're going to learn about something called diagonalizing matrices, right? And we're also going to learn how to actually find determinants based off of the diagonal of a matrix, right? So it'll actually be very useful for us to know what the relationships are along the main diagonal. So you can carry out the multiplication. It'll always work to carry out the multiplication. The calculator understands the operation power 3, but it's very misleading because these are zeros, so it doesn't really tell the true picture. But it's very misleading because it might seem like you could actually just cube the entries or raise it to whatever power you want, but that's not necessarily the case. Okay? But along the diagonal, for Roman numeral 5, it's called an identity for a reason. All right, the subscript just tells us the dimensions. All right, identity matrices are always square matrices, so we're looking at something that there's only one subscript there. That's because it has the same number of rows and columns, so we're good to go.